Hello, welcome to the course PH5BO6 Electrodynamics 2. The contents of today's lecture is taken from Fundamentals of Magnetism and Electricity by D.N. Vasudeva. We'll continue to discuss topics from Chapter 22, Alternating Current Circuits. In the previous class, we have analyzed the behavior of AC through an ohmic resistor, where we have seen that both current and voltage are in phase. Today let's try to understand AC flow through an inductor. So consider an inductor of inductance L, which is connected to an AC voltage source of voltage E equal to E0 sine omega t. What happens here, the AC voltage tries to drive current through the inductor. When current flows through the inductor, there is a back EMF developed against the current flow, and the back EMF magnitude is minus L into di by dt. So back EMF tries to oppose the current flow. So if you want a steady current to flow through the circuit, the applied voltage should overcome the back EMF. So let's look at the situation where the applied voltage is exactly equal to the back EMF. So from this point, if you increase the applied voltage slightly, you will have a steady current flow through the circuit. So this is like the starting point of a steady current flow. So you can call this as a steady state. So this is a common technique in physics. Whenever we try to analyze the behavior of a dynamic system, you know that in a dynamic system, a lot of parameters are changing as a function of time. So it's a bit complicated to understand the overall behavior of the system. So what we do is we choose a steady state condition where there is some sort of an equilibrium, then try to understand the behavior of the system from this steady state perspective. So here also, if you look at the current, initially when the applied EMF was fighting against the back EMF, the value of the current keeps changing. But once the applied EMF is greater than the back EMF, you will have a steady current flow. When I say steady current flow, I know we are talking about AC currents here. So the instantaneous value may be changing sinusoidally, but if you look at the average value or the RMS value, from the steady state onwards, the RMS value is going to be a constant. So at the steady state, applied EMF is equal to back EMF. So I can write E0 sine omega t equal to L into di by dt, or di by dt equal to E0 by L sine omega t. Integrated, you get I equal to the integral of sine omega t is minus cos omega t divided by omega. So current I equal to minus E0 by L omega cos omega t plus a constant k, because we are doing an indefinite integration. Since we are talking about steady state currents here, I can conveniently put k equal to 0. Then the value of current is going to be I equal to minus E0 by L omega cos omega t. Minus cos omega t I can write as sine omega t minus pi by 2. Also, look here, I have a term E0 divided by L omega, where E0 is the peak applied EMF. This factor L omega is known as inductive reactance XL. Usually when you have a DC flow, you use the term resistance, and when you have an AC flow, usually we use the term reactance. So inductive reactance XL is nothing but the resistance offered by an inductor to an AC flow. Or in terms of the linear frequency F, I can write XL equal to 2 pi FL. So this is the resistance offered by the inductor to the AC flow. The inverse of reactance is known as susceptance. So let's rewrite this equation in terms of the reactance now. So if you look at this term, E0 divided by L omega. So this is nothing but peak voltage divided by resistance. We know that voltage divided by resistance is current. So peak voltage divided by the AC resistance is nothing but peak current I0. So the expression for current becomes I equal to I0 sine omega t minus pi by 2. Now, if you compare the voltage and current, you can see that the current lags the applied voltage by an amount pi by 2. Or alternatively, you can say that the applied voltage leads the current by pi by 2. So the relation between current and voltage you can pictorially represent either using a waveform diagram or a vector diagram here. So let's first look into the waveform diagram. First plot E equal to E0 sine omega t. X-axis is omega t. So when omega t equal to 0, sine 0 equal to 0. So this is your starting point. At pi by 2, sine pi by 2 is 1. So you reach the peak value E0 here. At pi, sine pi is 0. Once again 0. At 3 pi by 2, sine 3 pi by 2 is minus 1, so you reach minus E0. Finally at 2 pi you come back to 0. So this is one complete cycle, 0 to 2 pi. Now plot the current for the same cycle. So when omega t equal to 0, you have sine minus pi by 2, which is minus 1. So you start at the point minus I0. When omega t is pi by 2, pi by 2 minus pi by 2 0, sine 0 equal to 0, so you reach the 0 point. When omega t is 3 pi by 2, then you have once again sine function giving you sine pi by 2, which is 1, so you reach the peak value I0. Then when you are at 2 pi, then you go back to the minus sine 3 pi by 2, which is minus 1, so you get minus I0. So if you look at the starting point, you can clearly make out that the voltage is leading over the current. But if you look at the course of flow here, by the time the current had traveled pi by 2 and reached the point 0, the voltage had already gone ahead and reached the peak value. And by the time the current travels another pi by 2 and reached the peak value here, the voltage had gone ahead and touched upon the 0 value. So at every point, the voltage is leading over the current by an amount pi by 2. Or alternatively, you can represent this relation using a vector diagram. As you know, current and voltage both have magnitude and direction, so they are vectors. And the phase relation or the phase angle between the two vectors you can represent as the angle between the two vectors here. So typically, a counterclockwise angle as shown in the figure represents an angle of lead, and a clockwise angle represents an angle of lag here. You see, there is a counterclockwise angle of 90 degrees between current and voltage, which means voltage leads current by 90 degrees or pi by 2. Now, coming to the inductive reactance once again, let's try to understand what is the behavior of an inductor towards DC flow and an AC flow. So if you look at the expression once again, XL equal to 2 pi FL, when you consider DC flow through an inductor, in the case of DC, the frequency F is 0, so consequently, the reactance XL is going to be 0. If you take an inductor coil with negligible internal resistance, then DC flows through the coil without experiencing any resistance. So you have a perfect flow of DC through an inductor. On the other hand, in the case of AC, you know that AC has a non-zero frequency, so consequently it's going to experience some amount of resistance. Since an inductor resists or chokes at the AC flow, it is known as a choke coil. As you can see, make out from this expression, when frequency is higher, the reactance is higher, and the frequency is lower, the reactance is also going to be lower. Now, this kind of a behavior where a chalk coil is able to selectively apply resistance to an AC flow has certain applications in electrical circuits. Because if you look at a AC signal, there are two ways you can control the AC flow. One, the conventional method of applying an ohmic resistor. Two, as we have seen here, using a chalk coil. Right. Now, if you are using an ohmic resistor, what happens? Whenever current flows through a resistor, there is going to be some sort of power loss associated with Joule's heating or heat dissipation. We have discussed this in the previous class. If I is the current through the resistor and R is the internal resistance of the resistor, then the power loss is going to be I square R. So this is inevitable. So a part of the energy is always lost. On the other hand, if you are using a chalk coil, like the one shown in this figure, to control AC, there is some advantage. Let's try to understand the power relation using this waveform diagram. We know that power can also be represented as a product of current and voltage, P equal to IV or IE. So we have one complete cycle here, 0 to 2 pi. Divide this into 4 quarter cycles, 0 to pi by 2, pi by 2 to pi, pi to 3 pi by 2, 3 pi by 2 to 2 pi. Okay. Let's try to calculate what is the power in each of the quarter cycles. In the first quarter cycle, you can see current is negative, voltage is positive. So current into voltage, the power is going to be negative here. In the second quarter cycle, from here to here, you can see both voltage and current are positive. So you have the product of these two being positive. So I have positive power in the second quarter cycle. Coming to the third quarter cycle, from here to here, you can see voltage is negative, current is positive. So once again, its product power is going to be negative. In the final quarter cycle, you can see from here to here, both current and voltage are negative. So the product is going to be positive. So I have negative power, positive power, negative power, positive power. Now, from the perspective of the chalk coil, what is the positive power means? Positive power means the source is transferring power to the inductor. Inductor uses this power to develop its magnetic field. On the other hand, negative power means the inductor is giving back the power to the source. So in each quarter cycle, the source transfers power to the chalk. In the next quarter cycle, the choke transfer the power back to the source. So this keeps repeating. So power is continuously transferred between the source and the choke, and if you make sure that the internal resistance of the choke is negligible, then this power transfer happens without any power loss. So in other words, whenever you are using an ohmic resistor to control AC, there is some amount of power loss. On the other hand, if you are using a chalk coil to control AC flow, then there is no power loss. So chalk is a more efficient option to regulate AC flow compared to an ohmic resistor. So that's about AC flow through an inductor. Next, let's try to analyze AC flow through a capacitor. So once again, I have a capacitor of capacitance C, which is connected to an AC source of EMF E equal to E naught sine omega t. What happens? Capacitor has two plates, so during one half cycle, one of the plates gets charged and other gets discharged. In the other half cycle, the first one gets discharged, other one gets charged. So plates gets charged and discharged continuously or periodically. So you have a periodic current flowing through the circuit. Or if you look at the charge Q stored in the capacitor, since the charge discharge cycle happens periodically, the charge stored inside the capacitor is also going to alternate. Now, if you take the potential drop across the capacitor as Vc, then I can write Vc as Q by C, where Q is the instantaneous value of the charge stored in the capacitor. Since I have a single capacitor connected across the power source, the entire applied voltage is going to drop across the capacitor. So I can write Vc equal to the applied voltage E0 sine omega t. From this I can write the instantaneous value of charge Q equal to C E0 sine omega t, or the current, which is rate of change of charge, dq by dt, equal to C omega E0 cos omega t. Cos omega t I can write as sine omega t plus pi by 2, and this particular constant E0 C omega I can also write as E0 divided by 1 by C omega. Okay. So both are equivalent, right? Now this particular factor 1 by C omega is known as capacitive reactance. So this is the resistance offered by a capacitor to an AC flow. Or in terms of linear frequency f, I can write xc equal to 1 by 2 pi fc. Now going back to this particular term, E0 divided by 1 by C omega, which is nothing but E0 divided by Xc. So this is peak voltage divided by reactance or resistance, which is nothing but the peak current. So we can write the instantaneous value of current I equal to I0 sine omega t plus pi by 2. If you compare this with the applied voltage, you can easily make out that the current leads the applied voltage by pi by 2, or the applied voltage lags the current by pi by 2. So once again, you can represent this phase relation either using a vector diagram or a waveform diagram. So in the vector diagram, I have applied voltage along the x-axis, current along the y-axis, then I have a counterclockwise angle of 90 degree between them, meaning current is leading over the voltage by a phase angle 90 degree. And this is the waveform diagram. So you have E equal to E0 sine omega t represented by this black curve, and I equal to I0 sine omega t plus pi by 2 represented by this red dotted line. And from, if you look at the starting point, you can clearly make out current is leading over the voltage. So by the time voltage had traveled pi by 2 and reached the peak value, the current had already gone ahead and touched upon the zero value. So at every point you can see that current is leading over the voltage. Now, once again, coming into the specific features of the capacitive reactance. So let's try to understand how does this reactance work with DC and AC. So if you look at DC, frequency is 0. So if you substitute F equal to 0 in this equation, you get the capacitive reactance Xc equal to infinity. So whenever DC flows through a capacitor, it experiences infinite reactance. So as a consequence, the DC signal gets completely blocked by a capacitor. So this is very, very important. On the other hand, in the case of AC, the frequency is non-zero. So it's going to experience some amount of resistance depending on the frequency. So when the frequency is more, you can see from this equation, the reactance is less. On the other hand, when the frequency is less, the reactance is more. So the capacitor allows AC with some amount of resistance. Now the ability of the capacitor to selectively apply resistance to an AC flow is utilized in filter circuits. So you have different types of filters like high pass filter, low pass filter, and band pass filter. So how does a capacitor work as a filter? For example, if you take the case of a high pass filter, suppose you have an incoming signal which contains a high frequency component and a low frequency component. So you allow this to pass through a capacitor. What happens? For the high frequency component, the resistance or reactance is low. So the capacitor allows the high frequency to pass through. For the low frequency component, the reactance is very high. So capacitor kind of blocks this low frequency component. So here the input contains both high frequency and low frequency, but the capacitor allows only high frequency to pass through. So this is the working behind a high pass filter. So similarly, you can engineer your electrical circuit and allow only low frequency to pass through the capacitor, or low frequency to pass through a particular point beyond the capacitor. So that is known as a low pass filter. Similarly, you can choose a particular frequency range to pass through a particular point in your circuit. So this will be called as a band pass action. You can also use the capacitor as a bypass line. For example, suppose you have an electrical signal coming at this point. So it has both high frequency and low frequency components, and you have a load resistance here, and you don't want your high frequency component to go through the load resistance. So basically you want to bypass this load resistance. So what you do, you connect a capacitor in parallel. So at this point, when the high frequency signal looks to both resistance and capacitor, here there is a high resistance. On the other hand, at the capacitor end, the resistance is low. Current always chooses the path of least resistance. So the high frequency components goes through the capacitor, completely bypassing the load resistance. So this is known as a bypass capacitor action. So you can use a capacitor either as a filtering component or as a bypassing component. You can use the selective reactance of a capacitor in your oscilloscope. So when you use oscilloscope in your lab, you will find a button in your oscilloscope which shows DC, AC and GD, which is the graph. So basically here your AC signal or DC signal is coupled into oscilloscope either through a capacitive network or like directly. So let's understand what is the difference between a DC coupling and AC coupling. Once again, assume a general scenario where your input signal has both AC and DC component. So if you press the button into the DC mode, basically DC coupling is activated. Here what happens is the signal is given directly to the oscilloscope. So you have a sinusoidal signal here, and also you have a DC component, say 2 volt DC component. So what happened? This is 1 volt, this is 2 volts. So you have a DC line established here, 2 volt. On top of that, you get an AC signal. So this is DC coupling. On the other hand, if you push this button to the AC point here, the AC coupling is activated. So here what happens is your input signal is not directly given to the oscilloscope. In between, there is a capacitor here. So the input signal containing both DC and AC is given to this capacitor circuit. So what happens? The capacitor blocks the DC and allows only the AC into the oscilloscope. So previously you had a 2 volt DC, on top of that there is an AC signal. Now in AC coupling, this DC component is completely removed, so your baseline comes to 0, and on top of that you get your AC signal. So whenever you want to remove the DC part and want to view only the AC component, then you can use the AC coupling mode here. This will be particularly useful when you are dealing with signal which has a very strong DC component and very feeble AC component, like a flipper around a strong DC component. And here, so when you use AC coupling, you can get rid of the strong DC. Now there is a very weak AC signal. You can enlarge this by adjusting the voltage and time settings here and view it. On the other hand, if you have both DC plus AC, when you enlarge it, your DC component is already very strong. So when you enlarge the signal, which is going to go out of the range of the screen. So whenever you want to view a very feeble AC signal associated with a strong DC signal, you can use AC coupling. Just for the sake of completeness, I will also say what does this ground mean. When you use ground, basically this oscilloscope, this point is connected to the ground. So irrespective of the signal you give here, you are going to see only a baseline at the 0 here. Basically no signal will be shown on the screen. So that's about AC and DC coupling in your oscilloscope, and you will use this function extensively in your lab practical. So since that now you understand the working of a capacitor behind this coupling circuit, whenever you use oscilloscope, you can use it in a more effective manner. Okay. So that's about AC flow through a capacitor. In the next class, we will discuss AC flow through an LR circuit, which is a combination of an inductor and a resistor, and also a CR circuit, which is a combination of capacitor and resistor. Thank you.